Welcome to this presentation in which we will present some design examples. In a previous video, we discussed how to design filters using pole zero location. In this talk, we will consider a filter that has a pole at omega equals 0. We will consider another example in which we will add a 0 at omega equals pi. We will discuss which is a better low pass filter. We will show body plots using Scilab code. Let us consider this simple example, a filter whose transfer function is g1 of z equals 0.5 divided by z minus 0.5. g1 has a pole at z equals 0.5. Recall the characterization we made earlier. We called this the low frequency, we called this the high frequency. The pole is z equals 0.5 is in positive real axis, which is the low frequency region. So g1 is low pass, it magnifies frequencies near omega equals 0. The steady state gain of g1 is 1. Why do we call it the steady state gain? Remember, y is equal to g1 into u, where u and y are z transform of input and output respectively for the filter. The steady state value of u is multiplied by that of g, so we call it the steady state gain. Let us continue with this filter. Let us substitute z equals exponential j omega. Why do we do this? Recall the way we defined z transform. We take z transform and substitute z equals exponential j omega. So we get g1 of exponential j omega. In the place of z, you substitute exponential j omega. Let us simplify this, expand this into cosine and sine as given here, and separate real and imaginary parts, multiply by complex conjugates. One can simplify to get this. One can also get directly from here the magnitude of 0.5 is 0.5. The magnitude of denominator can be checked to be this, and the phase of this can be obtained as this. You have to do a little bit of calculation to arrive at this. The argument can also be calculated directly. This is the imaginary part, this is the real part, so you get sin omega divided by cos omega minus 0.5. Of course, this minus sign is here, so you have this minus sign, tan inverse of this. So let us draw the body plot of this low pass filter, and it is the solid line in this plot. What is the dotted line? We will see it in a subsequent slide. This filter magnifies the signal frequencies near omega equals 0. The magnitude is 1 here. Now we will consider another example. To the g1 that we considered earlier, let us add a 0 at z equals minus 1. We already had a pole at z equals 0.5. Now we will add a 0 at z equals minus 1. The factor 0.25 is included so as to make the steady state gain of g2 1. You can verify this easily by substituting z equals 1. So this also has a pole at z equals 0.5. This pole amplifies low frequency components. In addition, it has a 0 at z equals minus 1. We know that the 0 filters high frequency components. Recall that g1 does not have the 0. As a result, g2z should be a better low pass filter. Let us verify it now. So this is g2 of z. Let us evaluate at z equals exponential j omega. I have taken this 0.25 on the left hand side. For z I have substituted. Now split this into sine and cosine. So this is the numerator term. Similarly, the denominator term. Now what we will do is take the numerator and group it into real and imaginary parts. Multiply both sides, both numerator and denominator, by the complex conjugate of the denominator. So this is the complex conjugate of the denominator. Now what happens to the denominator? So we get this real term when we multiply by complex conjugate. One can simplify this, okay. I am going to let you do that. You can verify that this term is equal to this. Please work out this calculation. G2 that we discussed in the previous slide, the second example, has the Bode plot given by broken lines. Note that the magnitude of G2 is smaller than that of G1 at high frequencies, especially at pi. At pi, in fact, the magnitude of G2 becomes 0 because we have a 0 for G2 of Z at Z equals 1. So we say that G2 filters high frequency components better. In other words, we can say that G2 is a better low pass filter. So let us summarize. G1 has a pole at Z equals 0.5, G2 has a pole at Z equals 0.5, and in addition a 0 at Z equals -1. This additional 0 helps reject high frequency components better, as we saw in the Bode plot given in the previous slide. Here is the Scilab code for this, where we define G1, G2, calculate magnitude and angle for 2, similarly calculate magnitude and angle for filter 1, plot them both in the same plot. Let us now see the Scilab code. I have put some commands in the Scilab directory, so I get the whole directory and then I execute this file filter1.sce, and it gives me the Bode plot as we see here. This is exactly the plot that I showed in the previous slide. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.